All right, it's my pleasure to introduce our next speaker, Bernhard Thomaszewski. Bernhard is currently a research scientist at Disney Research Zurich. Before that, he was a postdoc at ETH Zurich, and before that, he was a PhD at University of Tübingen. Bernhard's an expert at fabrication, simulation, design, this kind of area, and he's going to talk about that today.
Thank you very much, Jen. Actually, what we forgot to mention is that we have a bit of a common history, right?
That's right. You actually came to visit University of Columbia when I was a PhD student there.
I was just going to say that that's how we know each other.
Yeah.
Thank you very much for the introduction, and thanks for inviting me. It's great to be here. I see that I have a lot of space to walk around, which is really great. So I'm going to talk about inverse problems in computational design. The type of problems that you encounter all the time if you're looking at application-oriented design. But before we get to the inverse problems, I just want to talk a bit about why we're interested in fabrication to begin with. And obviously, design for manufacturing is important for pretty much all industries. But something that I also like a lot is that fabrication or making things is a great way for end users to be creative. And oftentimes you only need very little to express like a creative idea to translate it into a tangible physical artifact. Now, there are many different ways and materials and many different processes of making things. And oftentimes it's the material itself that inspires us to come up with beautiful designs that are complex or that even have some interesting functions. But as we go to more complex designs, as the designs get more and more intricate, the manufacturing itself, the making of the thing, becomes more and more of a problem that exceeds, well, the means and also the skills of users. But now there's a new tool on the horizon, right? 3D printers. They basically hold the promise that all the difficulties of conventional manufacturing are just going to be removed at once. You don't have to glue anymore. You don't have to mold or mill or weld. All we need is a 3D digital design file, and the 3D printer is going to make that file at the push of a button. That's the vision for it, right? Now, to what extent actually the consumer level printers that we have right now can live up to that expectation is a bit of a different question. But the principle itself of 3D printing definitely has some really striking and interesting advantages of conventional manufacturing. And perhaps the most important advantage is complexity. We can make things that are incredibly complex, much more complex than what we could ever do with conventional manufacturing. In this example that you see here on the left-hand side, right, that's a load-bearing engine block that was optimized, well, designed automatically to have an optimal strength-to-weight ratio. And you can see that it would be really impossible to get into all the cavities with a tool. You couldn't mold it. Really, the only way to do it is using 3D printing. And something that's also interesting in this context is that when you make such a design that's as complex as this, it doesn't even cost you any more time or money to make it. If anything, it costs you less because you need less material compared to just a solid block of that same material. Now, in addition to geometric complexity, we can also combine different materials and create a material complexity level. For example, we can mix different colors. That's great, but maybe not as exciting as it can get. We can also use different material properties like elastic stiffness or conductivity, many different things. So that's actually, well, I would say that 3D printers are pretty amazing. If we look around on the internet and search for like 3D printed objects that average people make, then the results are sort of underwhelming. People generally like to print out colorful models of like random objects that are static, they don't do anything. You can put them on the shelf, they look beautiful. Maybe you can make replacement parts, but that's pretty much it. So this use of 3D printing is really not using the potential of 3D printers, not even close. So instead we could use 3D printers to create models that actually have a useful function. For example, mechanical toys, mechanical automata. We could create custom input devices that can be deformed in prescribed ways, and that are also able to sense the information at the same time. Or we could combine 3D printing and off-the-shelf components to create things like robotic creatures. I mean, the sky's really the limit. We can do so many things. But the problem with all that is, when the design gets more and more complex, it becomes more and more difficult for us to create these designs, right? So an average user, for example, wouldn't be able to create a mechanism that moves in a desired way. That's a difficult problem. do that, but even they have to spend a lot of time just tweaking the parameters of the mechanism, like the length of the bars, how should they connect. A lot of time goes into that. Valuable time that they could use instead for, well, what they're really good at is being creative and problem solving. So to bring this to a very concise and brief point, the tools that we're currently using, yesterday's software fails today's hardware. We really don't have the tools available to leverage the full power and potential of 3D printing. So what we've been looking at over the past 4 or 5 years at Disney Research is like ways of coming up with better tools, like new ways of designing things. That these tools, well, what they do, they leverage computation in order to automate the parts of the design process that are difficult for an expert engineer and for an average user alike. So all these design tools are different. I mean, each application, each design problem has its particular challenges. But there's somewhat an underlying structure that is common to most of these problems. And I would like to illustrate that structure on a simple example, one that I actually like a lot. Let's say we wanted to make inflatable rubber balloons that inflate to desired shapes. So how would you go about making such a balloon? I don't know if you've ever tried to make your own balloon. It can be done using latex, it's not so difficult. But if you wanted to inflate to a shape that you have in mind, what's the uniform shape for a balloon? That's a difficult question, right? So the first thing that we need when we make a computational design tool for such a problem is we have to have a computational model of the phenomenon, the physical phenomenon that we want to reproduce using a computer. In this case, if we're talking about rubber balloons, we're looking mathematically at something that's like nonlinear specifically, so we could do like a continuum mechanics approach and discretize these equations with finite elements. That's pretty much all standard. And at the end of all that, we get a simulation tool that allows us to map from the system's parameters to the resulting state. In this case, the parameters, that's the shape, the undeformed shape of the balloon, and the inflation pressure, and then the system state, that's just the deformed state. What you can see here is that, well, if you make a simple guess, like, oh, let's try and start with a small-scale version of the target, that doesn't really do the job, right? So for this instance of computational design, we're not asking, oh, here's parameters, what's the resulting state? We're asking the much more difficult question, here's the desired state, what are the parameters that take this as close as possible to this state? So we have to go sort of the other way around. We have to convert the simulation, and that's exactly what I mean when I say inverse problem and solving inverse problems. So how we do that concretely is using optimization, numerical optimization algorithms, and we'll spend a bit of time looking at some of those in more detail. I will admit that this is a bit of an experiment because I haven't done that in such a context before, and if I lose you, just let me know, and I can slow down or accelerate or whatever is appropriate. Well, but anyways, so the result of the optimization process is then an optimal design that we can use, well, for whatever fabrication process we have available, and well, that's the final product, the final design. Now, so if we look at this in a more broader context, there are really 3 important components of a computational design. One, we have to have the computational model, the simulation tool. But then we need to be able to invert that computational model, the inverse problem, and we do that with optimization algorithms. And last but not least, or not in any way less important, we also need to have something like a graphical interface that allows the user to specify design goals, because most of the time, or very often at least, it's not just a one-off thing where the user says, oh, here's what I want, make it and I'll be happy with it. So the interface needs to support the exploration of the design space by the user. And that's also a very challenging problem. But today I thought we just look at how to solve for the model, how to solve inverse problems. It's awfully quiet in here, actually. Any questions so far? Okay, so to make these things more concrete, I thought we'd look at a very simple example. The 2D elastic bar. We'd assume that this elastic bar is already discretized. It's represented by a 2D triangle mesh. And the undeformed state of this bar, we call that P. That's just a vector, a state parameter vector that holds for each vertex in its mesh its rest position. Well, let's say we have n vertices, right? We call that P actually because later we'll say parameters. These are the parameters of our problem that we can change in order to change the state. Now, if we don't apply any forces, nothing will happen to the undeformed state. But as soon as we have external forces, such as gravity, then that bar will bend downward, right? And that deformation, well, we can compute it, we can simulate it, basically, using our computational model. So what's interesting is that, and it's also obvious, I guess, if we change the undeformed state, the parameters, then we will observe a different deformed state. So this simple observation, what I want to say with this is just like, if we change the parameters in the right way, we might be able to create the desired deformed state, or whatever it is that we want. For example, we could say, oh, we want actually the deformed state to be a straight bar again. So what's the shape that will satisfy this requirement? Now, before we can talk about how we optimize our computed parameters, that'll be this job for us. We have to have a computational model that tells us basically how we get from parameters to state. And we'll try to do that in as simple a way as possible, just looking at generalized springs in order to describe the internal forces that the deforming bar will produce in order to counteract and oppose external forces. So we'll just look at a random spring here, basically in its deformed and undeformed configuration. The undeformed one, again, is defined by P. The deformed one is defined by the position x. And go back because this is very cluttered. So we can compute the deformation of the spring in a very simple way. It just has the ratio of its current length and its initial length minus 1. If that deformation is 0, well, that means the spring is not deformed. If it's smaller than 0, the spring is compressed. If it's larger than 0, the spring is stretched. From this deformation measure, we'll now try to set up an energy. And the simplest way of doing that is just to say, like, well, it has to be at least quadratic in the energy, in the deformation. So that's what we're going to do. We're going to square this deformation, and then we'll integrate it over the spring, which, when we assume that the deformation is constant on the spring, just means that we multiply it by the rest length of the spring. Once we have this energy, that's a function of both the deformed and the undeformed position, we can compute the forces that the spring exerts on the points just by taking the partial derivatives, the gradients, the negative gradients of the energy with respect to, well, the deformed position xi and xj. So that gives us a simple spring a force for one spring, and then if we want to know the total force at a given internal load, it's just the sum of all the springs. So I haven't really said anything that you're not aware of. It's really, really simple. But the only thing that I want to point out here is that, well, we can take derivatives of the energy with respect to deformed positions, but we can also take derivatives of the energy with respect to the undeformed position and mix derivatives, and we're going to need all that later on. Okay, now that we have the internal forces and the external forces, which is all, we are basically all set to just state the equilibrium conditions that govern this elastic bar. Pretty much just like, oh, if a system, in order for a system to be at equilibrium, the total forces have to vanish in every node. They have to sum to 0 everywhere throughout the entire structure. Again, that is not surprising, but what's interesting to note here is that, in general, this is a system of nonlinear equations. Even for a simple example like this elastic bar, where we try to be as linear as possible, it's directly nonlinear. Well, we can solve the system of equations using Newton's method, and that way we obtain, for a given set of parameters, the deformed state. But so what if we don't like that deformed state? We want it to be something else. What do we do? Well, first of all, we have to be clear about what is it actually that we want. So we have to prescribe an objective, like a target, or a distance energy that measures the distance from our current state to where we want to be. So the first thing to do is like have a target shape. That could just, again, be a mesh, right? And then a simple way of measuring the distance from our current state to the target, that would just be to say, like, I'm going to loop over all the points and measure that pairwise distance between the deformed position that I have and their target position. It's just a simple L2 norm. It doesn't get any simpler than that. But with this objective set up, we're actually now ready to formulate the inverse problem, right? Now we're asking, what are the parameters such that the resulting deformed position are as close as possible to the target shape. Or put more formally, we want to minimize over x and t the target energy t of x. We want to minimize that, subject to the constraints that the elastic forces, well, the total forces have to be 0 at every node. That means we want to find P such that X makes sense in the sense that it's an equilibrium configuration. So that's like sort of the template version of the inverse problem and its constraint-based formulation. This, by the way, is the solution to that particular case. I don't know if it's immediately obvious to you, but it's actually just the reflected, symmetrically reflected version of the deformation, which of course makes a lot of sense in this case. So that problem is actually trivial, but only for this specific instance of it. We might, for example, ask for a target shape that is not physically feasible, and then the challenge is to find something that's as close as possible to it. But the good thing about it, it's an easy problem. We know the solution, so we can evaluate different ways of optimizing or solving that problem in a more generic way. And that's what we're going to do next. So there's really a wide range of methods that we can use to solve constrained optimization problems, such as this one here. I'm just like, from the top of my head, I just listed like the 5 that came to my mind immediately. One thing to do is randomized search of some versions of it, like CMA, for example, simulated annealing. Like we could just guess the parameters, or guess the parameter vector, see if it does any better than what we currently have, if it does accept, if not reject. Very simple, but incredibly slow, right? Methods that are just below there are more advanced and potentially much more efficient, but I'm not going to talk about all of them here. I just want to focus on two variants in a bit more detail. The first one is so-called sensitivity analysis. Who's heard of sensitivity analysis? Anybody? Okay, that's about 3%. Okay. And the second one is sequential quadratic programming. Have you heard of SQP? Yeah, okay. So maybe sensitivity analysis is just a matter of like, nobody has a better name for it. People call it implicit function theory-based optimization. Okay, anyways, let's start with sensitivity analysis. So as I said before, apologetically, this is going to be a bit heavy on equations. And if I lose you, let me know. All right? Good. So we have that simulation. We've defined it on the previous slides, basically. And it provides us a map from parameters to corresponding state. So another way of saying that is that, well, X, the deformed state, is actually a function of the parameters. The problem is that this function is only implicitly defined. We have to solve a set of nonlinear equations. We don't have it explicitly available, so we cannot take derivatives of it or just solve that resulting expression analytically. That's not possible, at least not in the general case. However, what we would like is to actually have an explicit expression that tells us how a given state and parameter relates to a corresponding state and change. Right? If we have that map, that would be great. So what we do know is that whenever we change the parameters of the system, then the deformed positions, the state, has to change accordingly in order to satisfy the conditions of equilibrium. That means that F force, total force, has to be 0 at every node all the time. Cannot be violated. That's the condition that we need to satisfy, and we can rely on it in physical reality. Now, another way of saying that is actually to say, like, when we think of changing parameters, then we know that the total derivative of the force with respect to parameters, that needs to be 0. Right? I change the parameters, force needs to be 0. So if we split that up into the partial derivatives, then we can identify an interesting term, or well, the term that we're actually interested in. dx dt, that's the map that transforms a state and parameters to a corresponding state and change, at least the first order. So that's all we need. From this we can just rearrange terms, and then we arrive at this expression. Well, we have to invert the matrix. In practice, we actually don't invert the matrix. We solve a set of series of equation, the same matrix as the system matrix. But anyways, we have a clear way of computing dx dt. dx dt is also called the sensitivity matrix, like the sensitivity of the system's output with respect to parameters, and I guess that's why people Yeah, so great. We have dxdp. What can we do with it? Well, from dxdp, we can actually compute the gradient of the objective function, right? Because we want to arrive at a point where the objective function is minimized, the distance to the target. So how we do that is, well, we can just use the chain rule, very simple. dt dp is just dt dx times dx dp. All weird transposes coming in whenever you have matrix calculus, yes?
So whenever I read the papers, it seems that people just usually assume that sensing matrix is full rank. Is there a reason why this is usually true? Is there a tradition for that?
That's a very good question, yeah. No, I wouldn't say that it's true in general. In our case, well, for a specific problem of like the 2D elastic bar, I would say it is true, because whenever you change the rest position in the equilibrium mesh, there's going to be a corresponding change in the deformed position. So there's no combination of parameters that result in zero net change of the deformed state. So there's no this matrix is not singular in its full rank. Does it always have to be like that? Probably not. But I mean, chances are, if in general, probably you'll have, well, one easy way when it's not going to be like that is if you have more parameters, then decrease the freedom, but I'm not sure that this is a very useful case. Yes? Okay.
If you do something very symmetric, if you have a symmetric solution,
Yeah.
you have your bar and now you change your your initial state symmetrically, then it might not even affect, right? If you go up and down at some positions, and so due to symmetry, it would maybe not even change the state. So even
Yeah, I mean, it is true that there are instances where something like this can happen, but as I said, in this case, even if you symmetrically move points like left and right, in the deformed state, they'll also move left and right, right? And that way. So dx dt, right? We're not talking about, oh, wait, did you mean dt dp? No, you meant dx dp, right? For dx dp, I would say here, I'm positive it's singular, and it's non-singular. But if we're talking about dt dp, of course, there are combinations of parameter changes and state changes that don't change the target, the objective, right? Okay, anyway, where was I going with this? So yeah, we can compute the gradient of the objective with respect to the parameters. And, well, now we can do something simple like gradient descent, right? We can try to minimize the energy just by walking along its negative gradient. So we do that iteratively, and in each step we will first compute an appropriate, well, step in the parameter space, delta p. And for that we have to basically choose a scalar, how far we want to walk along the negative gradient. Once we have found that, we can just update the parameters. Once we update the parameters, we update the deformed state. Now, there are two things that are not as easy as I just made them sound. First of all, if we have a direction delta p, how do we compute the corresponding delta x? Easy, right? Because well, we have the xdp, so it's just a matrix multiplication. But the problem here is that is the linear approximation of something that's really non-linear in reality. So we're discarding higher order terms, but by discarding them, we're really introducing, well, a mistake or errors in the forces. Well, what I mean by that is that when we just do this update, in general, we'll arrive at a state that is not in equilibrium. And that's a problem, because as soon as we're not in equilibrium anymore, the forces are not zero, then our entire premise is like not valid anymore. We cannot compute dx dp in the way that we were computing it. So we have to be very careful about how we do the updates. It's the only safe way to do it in general is, well, you have to solve a static equilibrium problem. You can do that, but it costs. It takes time. Now the second thing to point out or to ask is like, if we know the gradient, we can compute it, right? Well, how do we know how long we have to walk along it, right? Well, here the idea is simple, like that's what people typically call line search. You start with an optimistic estimate for a step. And then what you want to do is you want to reduce the value of the objective function. So if your guess for the step does increase the objective function or not, decrease it at least, then you just like divide it by 2, let's say, or scale it by some other factor. And then you do that over and over again, so-called backtracking until you arrive at a point where the new objective is actually smaller than your point. That's not very complicated, but again, for each failed attempt that we're doing, we have to solve a system of equations again. nonlinear system of equations. And if you put all these things together, it's just a whole lot of nonlinear systems that we have to solve. And that can very quickly become a bottleneck. Now, from my own experience, there's not a lot that you can do to get around having to solve nonlinear systems, but at least you can try to be smart about how you choose the direction to begin with. You don't have to use the gradient, right? You can do something smart. You can do, for example, Newton's method instead of gradient descent. Well, what that means is that, well, we're at a given parameter configuration P. And let's say that the gradient of the objective is non-zero at that configuration. So what we're looking for is an update for parameters delta P such that at the new position in parameter space, the gradient is zero. You can just Taylor expand this and truncate it after the first order terms. And then we get a linear system of equations for computing delta P. So that is simple as a concept. But in practice, the problem is that, I know it's cluttered, I spelled it out for you, but what I want to point out here is that if you want to compute the second derivative of the objective with respect to parameters, there's something crazy coming in. The second derivative of x with respect to p, in principle you can compute it, but it's like computationally completely intractable. Even to compute dx to p, you have to solve linear systems, and this is like so higher order tensor systems, basically. And we cannot really do that in an acceptable time. But on the other hand, we don't really need the full Hessian to make a Newton method that works at converters, right? We can use an approximation, so-called quasi-Newton methods. For example, we can just say, like, we'll use only the first term of the real Hessian because that's only required dx to p, and that will work. But it turns out that in practice, what's really hard to beat is so-called BFGS, which makes an approximation of the true Hessian just from outer products of the gradient at different iterates, right? So you don't even need to compute dx to p fully. All you need to compute is this product between dx to p and dt dx. And from that, you can very quickly and at low cost construct an approximate Hessian, even an approximate inverse Hessian. So it's really a very powerful tool. So to wrap this up on sensitivity analysis, there are a few advantages that I would like to point out here. For one, it has the minimum number of variables, just the parameters. I don't think that you can do less than having the parameters. It doesn't have to state as a specific parameters, which means that at the end of the day, you only solve your linear systems of dimension p times p. That's good. If you're using BFGS, typically that has pretty good convergence, super linearly. Not as good typically as if you had the full Hessian, if you were doing real Newton. And then one other thing that's also nice about sensitivity analysis is that it scales quite well if you're using multiple targets. Why would you want to use multiple targets? Maybe not for inverse elastic design, but if you're looking at a mechanism, let's say, and you want to optimize the motion of the mechanism, then each time step of the kinematics of the mechanism is a new state. And it's just very convenient that the size of your system does not change with increasing number of targets. I mean, it doesn't get any cheaper, you still have to solve more systems of equations, but these are pretty much independent and can grow. So the disadvantages really with this approach is that you always have to be sure that the system is in equilibrium. F equals 0 has to hold all the time. So as a result, you have to be really careful about how to do the update to the delta x. We need to do simulation, we need to solve nonlinear system computation. And on top of all that, we need line searching, right? So yet more systems of equation to solve. BFGS helps that because we have a good direction, but it's still a lot of systems that we have to solve. So maybe if we do something else, and we get around solving some systems. Okay. Are we in terms of time? Okay. So what sensitivity analysis really does, that is not, did I say it's constrained optimization? Well then I lied, because it's unconstrained optimization. There are no constraints, right? We eliminated the additional variables using the constraints. So we transformed the constrained optimization problem into just non-constrained, non-linear optimization. But we don't have to do that. We can also just say like, oh, we can have both x and p as explicit variables of our problem, right? Hoping that way we don't have to solve non-linear systems all the time to get the relation between them. But when we do have them as independent variables, then we need to enforce the consistency between them, because at the end of the day, x and p have to be such that the resulting forces are zero everywhere, right? Now, this is again the standard, that's the standard form of just say oh, here's an optimization problem, constraint optimization problem. And one way to formalize this, a very common way, is to construct the so-called Lagrange function for this optimization problem. In this case, the Lagrange function would just be the sum of our objective function that we had before, the distance to the target, plus a weighted sum of all the constraints. And the weights, the lambdas here, are the so-called Lagrange multipliers. Now we have actually a set of degrees of freedom. I just want to summarize here to be sure that we're talking about that we're on the same page. We have the deformed positions, we have the parameters, and we have Lagrange multipliers as degrees of freedom. We need one multiplier for each constraint, and if you do the math, the arithmetic, you see that, well, that actually works out to 6 times the number of vertices, which is a lot. It's like 3 times more than sensitivity analysis. Yes?
What is sort of the number of vertices we're talking about? Like,
Oh, in this example?
no, I mean sort of the problems you're having from the design, and what is sort of usually the number of vertices?
Yeah, I mean, it can definitely become a limiting factor or a decision for why to use one optimization approach instead of another, right? But so I'll give one example later on where we use STP, and that was really essential that we have a small number of variables. So I don't know, some like say some thousand, 3,000, 5,000, no, which is not a lot. Still, right? It's not a lot. Okay, so x, p, and lambda, we call that s, the state vector. There is a little detail that I wanted to still mention here is that, well, we'll have to set up a regularizer of the parameters, basically just asking that the parameters that we compute or optimize for stay somehow as close as possible to what they were initially. And that's really primarily for numerical reasons. Otherwise, you're getting into trouble when you're solving the equations later on. Now, if you haven't seen this before, I don't know if you have, but then it might not be obvious to you why that is in any way related to our goal of solving the optimization problem. It's just like a function, right? Well, but the relation to that becomes actually quite clear if you look at the so-called optimality conditions, which just say like, oh, for a solution S to be the optimum of this problem, or the solution to the optimization problem, the gradient of this Lagrangian function has to vanish for all the parameters. Still not obvious, but if you look at the individual components, that becomes pretty clear. So the gradient of L with respect to the Lagrange multipliers, that's just the constraints. It needs to be zero, obviously. Any solution must satisfy all the constraints. Now the first component, the gradient with respect to x, is a bit more interesting. And what it really says is that, well, we have to find a weighted sum of the constraint gradients such that the resulting vector that we get from that, the linear combination, is exactly opposite to the gradient of the objective function. Another way of saying that is the objective function gradient has to be in the span of the constraint gradients. Now, why does this make sense? Just assume that, okay, we're at the optimum. That means we have the constraints are satisfied. And then the constraint objective is not in the span of the constraint gradients, right? But that means there must be a direction which I can go to increase, to improve on the objective without violating the constraints. And that is a contradiction to our assumption that we will opt for, right? So it has to hold. That is really just a very, well, it's a complicated way of saying these two gradients, they have to align. And lambda, basically, lambda decides for you, well, the constraint gradients and the objective gradient, they don't have the same length. So that's basically the degree of freedom that you have to solve for. How much force do you need to apply in order to satisfy the constraints? Same holds true for the gradient with respect to the parameters. Now, so that are the optimality conditions. If we satisfy them, we solve the problem. We say, well, how do we actually satisfy the optimality conditions? Well, similar to what we talked about the sensitivity analysis, if we have a state S that doesn't satisfy these conditions yet, the gradient is not zero, then we're looking for a delta S such that it becomes zero. We Taylor expand it, discard all the terms, we get a system of equations, linear equations for the delta S that we're interested in. Now this is the last thing that I showed, and it's really outrageous because it's so cluttered, and I apologize for that. But I'm just showing it to you because I want to point out a few things that I think are interesting. First of all, if you look at the diagram of this system, 3 by 3, because we have partitioned our variables into 3 components, the upper left block has the Hessian of the objective. That's really easy, right? If we have an 2 norm, that's just going to be the identity matrix. What it also has is the second derivative of the constraint times the Lagrange multipliers. Now, second derivative of the constraint, then in our case, that means like the third derivative of the energy, which is a bit funny or unusual. If you're just doing simulation, you never need that. But essentially what the Lagrange multipliers do is it's another matrix, it's a 3D matrix, it's a tensor. The Lagrange multipliers, they just go and like condense it, this slices down until you have this single matrix left. Well, that, as I said, it's maybe not so usual to have third derivatives of the energy, but on the other hand, they're not very difficult to compute, especially if you're using symbolic differentiation, which I highly recommend. Then that's just like as easy as the second derivatives. Okay, another thing to point out is that there's a block on the bottom right that is 0. And that implies that the system that we get, the resulting system, is going to be indefinite. It's going to have negative eigenvalues. And that's important because most of the solvers, linear solvers that you're typically using, probably can't deal with that. Like standard conjugate gradient doesn't work. Standard LU or LTL decomposition doesn't work. So you need to have, if you want to solve the system yourself, you need to have good solver for it that can solve indefinite systems that are additionally sparsely symmetric. One solver that does that for you is Paradiso, which is also part of Intel's MPL. But you don't have to solve this yourself, actually. You don't have to assemble a matrix. You can just use an off-the-shelf QP solver, whatever you like. I know people in geometry processing like MOSAC, and I think it's great. And if you use MOSAC, then you basically just have to feed it as input all the matrix blocks. It's going to compute a solution for you. It's also going to deal with inequality constraints, which I haven't even talked about here, so that's very convenient to solve this problem. Now that's basically a quadratic problem, right? So, yes.
So those third derivative terms really make me nervous. Is it possible to just drop these and do apply some new protection?
It's possible, yeah.
Does it work?
I mean, convergence can be really hard. And it's, yeah, okay, so since you mentioned that, I actually did, well, these meshes, these yellow meshes that I showed before, they were actually results of optimization that I ran, like, well, yesterday. And, well, I tried to drop these terms because I was like, it's just an annoying implementation, but I'm just going to do it without them again. But the conversion just drops by a lot. So even for a simple problem like this here, you really want to have these terms, or at least if you don't have these terms, then you want to use maybe again a BFGS approximation of the Hessian. That's going to be better than just dropping it, from my experience.
So similar to the gas-Newton algorithm, right, for nonlinearities.
Yeah. All right, so if it's a quadratic program, which means that, well, the objective is quadratic, constraints are linear, then we just have to solve one of these problems, these linear system of equations, and then we have, well, a delta S that takes us directly to the optimum. If that's not the case, then we have to iterate. We basically then apply Newton's method to the optimality conditions. Then, because the optimality conditions are non-linear, then we apply Newton's method, same as before, and the algorithm for that, SQP, in really grossly simplified terms, which is that in each step we solve this quadratic program using either QP solver or our own indefinite solver. We get a search direction, the delta S. But if the problem is nonlinear, well, not quadratic and nonlinear constraints, then we cannot just set S equals S plus delta S. That wouldn't work. We have to be careful how much we update the states along that direction. And again, we do line search, right? That's the same as for sensitivity analysis. But the intricate thing, the complication that comes in here now, is that instead of just being able to evaluate the objective, and we say like, oh, we want the objective to get smaller, we now have to balance between objective and constraints. And very often we will have to increase one in order to decrease the other. And who's to say when that's acceptable? Well, that's actually the merit function, so-called merit function, gets to say when that is acceptable or not. And these merit functions, that can be very difficult to find, design, set up. I think it's more an art than science, actually. But so that's definitely a problem or a limitation of SDP. But if you found a good one, well, you can solve for the admissible step of that and update the state accordingly until converge. Okay, advantages are if you use all the derivative information you have, then SDP can be really fast. Well, one reason for that is that people spend a lot of time and thought on coming up with really good performing QP solvers, and if you can just use the QP solver, that's going to make your algorithm overall very fast. Problem is a bit like if you're looking at nonlinear problems, or using line search and then merit functions, constructing it needs a lot of testing, treatment, and experimenting, which is really, it can be very frustrating. Another thing is that it doesn't scale all that well with an increasing number of targets. We already have 6 n variables for just one target shape. But as we increase the number of targets, we have to increase, well, we have to add unknowns, variables for the new undeformed state, for a new state of the system. And in addition to that, we have to have a new set of Lagrange multipliers that enforce the constraint in that new state. So in our case, we would be getting 4 n variables for each new target. And that quickly explodes to like sizes that are not tractable anymore, at least not at an attractive rate. Okay, so that was a very brief tour rushing through some optimization algorithms. And I really only scratched the surface. I probably left out very important detail. Fortunately, there are very good books on that subject, and I highly recommend the one by Nostradam Bright, and that's really good, and the one by Boyd on convex optimization is also fantastic. So if you're interested in that, check them out. They're both actually freely available online. Okay, so I have a bit of time left. Probably not enough to go through all of it. But I wanted to show 2 examples of work that we did in the past. And as applications, essentially, of sensitivity analysis and sequential quadratic programming. The first one is about physical characters. That's a problem that we got interested in when we looked at a mechanical automata, which are really beautiful mixtures of engineering and artistry, a bunch of rigid bodies joined together. And then a single trend creates some very compelling and oftentimes surprising motion. We wanted to have a system that would allow average users to do the same thing without any engineering or artistic background. And what we did is we said, like, give us a model as input. It should have all the articulations in place, but it doesn't need to have the mechanism that would drive the motion yet. The user then goes in and selects part of the model and sketches a curve while indicating how they want that part of the model to move. And then we have an automatic step that basically directly looks in the database of template mechanism. What is the type of mechanism that is suitable for that motion, and what are the precise parameters that get you as close as possible to the desired motion? So that's something that looks interactively. You just select one of the 3 candidates that you presented, and well, you can get pretty close to a motion like this. You do that for all the points on the body you want to animate, and pretty quickly you get to the design that you can actually then send to a 3D printer. I mean, I'm leaving out a lot of steps here, right? How do you connect the gears, and how do you make sure that they don't intersect the moving parts? But anyways, you have to design, you can 3D print it, and play it in physical reality. Now, the important or the most interesting part here is really the user goes in and sketches a curve for how they want the point to move. What's the mechanism that makes that happen, right? That's again a classical inverse problem. So for this inverse problem, again, we need a forward. We need a way to solve the forward problem. We need a simulation model. And in this case, in order to simulate a mechanism, what we do is simply multi-body kinematics, not dynamics. And in the multi-body system, we have a number of rigid bodies. They're described by position and rotation, degrees of freedom, and the connections between the rigid bodies, the joints, we model them as constraints that essentially just ask a point or one component has to be in the same world space as a point on a different component, like that. Let's say these constraints. To get the motion of the system, we don't have to solve the constraint optimization problem, because in the forward the forward version of this problem, there are only constraints, so we can cast it as a minimization problem, just minimize the residual of the constraint. And if the design is correct, then there is a minimum that is at 0 actually. If the minimum is not at 0, then something went wrong. All right, so that way we can compute the motion of the mechanism quite quickly, much faster than what this video shows. That's really easy. But what if we don't like the motion that we get from the mechanism, right? Well, then we can change the parameters of the mechanism and observe how they change the resulting motion. And you can see that the motion changes by quite a lot, just if you move the distance between the gears or you change the length of the individual bars. Quite a lot of change in the resulting motion. And I would say it's not really intuitive how a change in parameter affects the state, change in state. Okay, so the question is, so how can we actually not just go the forward way, but solve the inverse problem, right? Using simulation, we can go from S to P, but we want to go from, parameters to states. We want to go from desired state to parameters. And this is where our sensitivity analysis comes in. The constraints must be satisfied all the time, so we can say the total derivative of the constraints must be 0, and then we can compute ds dp. I'm using S now instead of X because they're rigid bodies, but it's the same thing that we've seen before, right? So we can numerically solve for the SDP. That gives us a gradient of the distance of our current motion to our desired motion. We feed that into BFGS to quasi-Newton, and then it's actually really fast. Here's an example of how fast it is. It's at least, well, it's not immediate, but it's interactive. And here's an example of the real performance, like the real rate of the system. You just sketch whatever curve you want, and then the method comes up with a mechanism that is suited for reproducing that particular motion. There we go. Here's another example for a lag that initially it doesn't really move like a real lag, but then you sketch a curve to indicate how you want it to move. The foot then with adapts to mechanisms such as to give you a motion that's pretty close to what you want. Okay, so sensitivity analysis in this case works very well, and yes.
So the sensitivity analysis works really well, but I imagine you have kind of some good initial guess for the combinatorics of the linkage or something.
Yes,
right?
we do.
How do you figure that out?
We do that's a very good question. What we do is, and that's also the same solution how we actually choose a certain type of mechanism, because that's a discrete problem as well, right? So it's well, I dare say it's a bit of a brute force approach. We just sample the parameter space of all the mechanisms in a given, like, let's say, confidence range of what makes sense. And then we take all these samples, it's a coarse sampling, we put them in the database, and whenever the user sketches a motion, we first say, like, oh, what's the closest motion? Give me that mechanism, or give me the three that are as close as possible to that motion, and then we optimize them. Yeah. And then there's also a question like, oh, how do you say which curve is closer to another curve? I could go on with that, but instead I'd rather move on and show you an example that we created with this cyber. It's printed in one piece. I mean, the sample actually, the prototype still exists, but it doesn't move anymore because that material flows over time. Now it's very bent, it's really sad. A lot of time went into it, it costs a lot of money. But yeah, 3D printers are not yet as ideal as we might have been. Okay, very quickly, I want to talk about the application for STP. And the application for that is the inflatable structures, which I like quite a bit, and we like quite a bit, I should say. Because, well, one reason for that is that you can use it for so many things, portable architecture, furniture. People like inflatable furniture, I don't know why. But certainly for balloons, and pretty much all scales, right? Macy parade balloons, gigantic, small scale, far milder balloons that you can sell in the parks and so on show and stage shows. There's really a large spectrum of inflatable structures. So if you think about how you approach the problem of creating an inflatable structure that inflates the desired shape, well, what's important here is that unlike the rubber balloons, we don't have like a 3D rest shape. We have to make these balloons by stitching together flat panels. Right? And then the question is how you have to choose the shape of the panels such that when you stitch them together, the shape can inflate it. The shape looks like what you wanted, but also the seams between the panels are in the right place where you want them to be, because, well, seams are very important for aesthetic reasons, but also because artists tend to use different colors for different seams, for different patches, and of course it's important that they end up in the right space in order to get the creature across. So we designed a tool for this purpose that's basically in an interactive fashion. The designer can just create a curved network on the surface of the target shape. That actually takes longer than the optimization, because probably we don't have a fantastic way of doing that. But anyways, once you have the seam network set up, then the optimization comes in and computes the shape of the flat panel such that when you inflate it, it looks as close as possible to the target. That's pretty fast, and is it fast enough for the design to actually iterate and say, for example, I need the ears to be better fleshed out, so give me one more patch there, right? You can just say like, oh, here's another patch, optimize for it again, and you do that. Now, what's interesting here is that, well, we need to be interactive because the designer interacts with the process. In order to be interactive, the underlying simulation has to be very fast. Now that is actually quite difficult because balloons do something surprising. You inflate them, you would say like, expect probably, oh, there's a lot of stretching when you inflate them, but we also get compression. The reason for that is if you look at a simple balloon, disc in front, disc in back, and then you compare, you look at the length of the line from the outer boundary to the inner center. If you inflate the balloon, then the point in the middle moves up, right? And in order for the line not to stretch, it has to move inward. That means the entire boundary has to move inward. It decreases the length, and it can only do that by wrinkling, because you cannot compress the material. It's inextensible and it's thick. So you get a lot of these wrinkles, these airbag wrinkles, very typical of balloons, I would say, right? So these are due to compression. If you wanted to simulate them in that detail, you need a very high resolution mesh. We're talking about 40,000 K vertices or something. And that's not really possible at real time, or to active rates. And in addition, these wrinkles, they do also something nasty. They introduce negative eigenvalues and definiteness in the system. So sorting the resulting system is also much more expensive than just well-behaved linear systems. So our approach to this was that instead of using a high-dose mesh, we will use an approach based on so-called tension field theory, which, in a nutshell, is just the principal way of switching off a material's resistance to compression at the onset of compression. And what you can see in this picture here, on the right-hand side, that's our model on the coarse mesh. And we don't get the geometry of the wrinkles, but as you can see by the red shading, we get the compression in just the places where we originally have wrinkles, and the overall shape is very well preserved. So with this model, we can actually just like formulate it as the typical optimization problem. Well, minimize distance to target, right? Subject to constraint needs to be satisfied, and then we feed that into SPP. One thing that I want to show here is that the panels, they can really undergo very large deformations, such as in this example here. Probably even surprising how they deform. I mean, I didn't expect it. It's like a generalized tennis ball or something like that. And in order for this to work, well, we have to remesh all the time, basically, because otherwise the geometry just deteriorates. But that works quite well even when you integrate it with SQP. Okay, here are a few more examples. And now I'm going to wrap it up. Sorry for running slightly over time. Well, I've talked about this problem, so I hope I could give you an idea of why they are important for computational design problems. If you want to research in that area, you might finally opt to use some off-the-shelf solver, but it's very important to understand what are the underlying problems and how you can solve them to select the right method. I said it already, I've only scratched the surface, and there's much more to talk about and to learn. And these two books are great references, but what I like a lot is that we have this development in graphics, looking more and more at like really fundamental questions and fundamental problems in computational design and in inverse problem solving. I'm just listing 3 papers here that I found particularly interesting. 2 of them are Disney Research Zurich, so you should check them out, or you should ask the tech. The other one, the first one, is just a very funky way of solving nonlinear equations, not based on. And I think there's much more interesting work to do on that context.
Thank you.